Hi, this is Kelly King doing the Physical Aspects of Nature poster presentation in regards to ultrasounds. We conducted our experiment on experiment 2, which was the distance between the emitter and detector. A little bit of background information. So waves consist in two forms. When it strikes a boundary interface or interface between two mediums, all or part of the wave is reflected. So displacement of the particle's compound is when the initial and reflected wave overlap in the same place or region of the medium. The change that occurs is dependent upon the type of boundary. Constructive interference is when the waves add up, therefore producing a larger absolute displacement, and destructive interference is the smaller absolute displacement. In Young's double slit experiment, a test is conducted from one single source of light being passed through two separate slits that interfere constructively and destructively. A unique pattern is produced from the wavelength of the light sources being passed through the separate slits. When identical waves are in phase, pure constructive interference is achieved. When identical waves aren't in sync or are shifted half a wavelength, this is where pure destructive interference occurs. So when light is passed through narrow slits, it diffracts into semicircular waves. Pure constructive is crest to crest or tuft to tuft, or pure destructive is crest to tuft, so it's a little bit out of sync. In our experiment, the goal was to observe the distance between two consecutive peaks in constructive wave interference, and in doing so, calculate the wavelength of the ultrasonic waves being emitted. This information will ultimately allow for the speed of sound to be determined. It was hypothesized from our experiment in experiment 2 that there was a direct relationship between the distance of the emitters and the detector and the distance between consecutive peaks in constructive wave interference. And therefore, as the distance increases, so does the consecutive peaks in constructive wave interference. So our method was as follows. We started at a distance of 30 centimeters, and we measured the delta change value of the constructive wave interference. And we did this by moving the detector up and down on our retort stand until the two distinct maxima would be established. We determined this by the largest Vmax readings on the DSO when the wave detector is at different heights. We have repeated this in 10 centimeter increments, so we started at 30 and we finished at 70 centimeters in order to have valid data, and we did 3 sets of repeats for each of the 10 for each of the 30, 40, 50, 60, and 70. So we had 3 of the same value results from the distances. So we then determined the wavelength. We had a frequency of 41 kilohertz. So we were able to determine the wavelength by calculating the formula that is found in Young's double slit experiment, and then we calculated the speed of sound by having frequency. So the speed of sound is frequency times the wavelength. So with our results, we found that there was a positive linear relationship between the distance of the emitter and the detector and the delta change in the distance in constructive peaks in the constructive wave interference. So we found that there was a direct relationship between the two, as you can see in the graph of our poster, that as distance increases, so does the delta change in Y. And in conclusion, we found that our results supported our hypothesis and thus supported Young's double slit experiment. And we were able to determine the wavelength as well as speed of sound by obtaining the delta change in constructive wave interference as well as distance and frequency. Therefore, it's concluded that we had results that supported our hypothesis and as well as the Young-Stokes experiment.